Okay, so the last part is section 2.4, part 3 on period change. Okay, so first thing is what a period change looks like when you write it as an equation. Okay, and the form that a period change has is y equals sine or cosine. And then in parentheses, this Greek letter is called omega, and it's in front of x. All that it stands for is a number. Okay, so when you have a number in front of x, that's a period change. So in this problem, we would say omega is 4. Which just means the number in front of x. In this problem, omega is 2. Okay, and that's how you can tell it's a period change. You're multiplying by a number, but the number is inside parentheses next to x. Yeah, it's a Greek letter. It kind of looks like a W. Yeah, it's a lowercase omega. And here's another one. Y equals sine 1/2 x.
Does the second one say y equals cosine?
Cosine 2x. Okay, so what I think we'll do is let's just list one of each type to make sure we know all 4 types.
Did you say we were allowed to have a cheat sheet?
Yep, you can make a reference sheet for the test if you want. Sure. All right, so now a phase shift. This is your phase shift. It would have a trig function, sine or cosine, and then in parentheses, something would be added. Usually we do pi, pi over 2, pi over 4. Okay, a vertical shift. That looks a little bit different. You're still adding or subtracting, but this time it's on the outside. That's a vertical shift. Okay, amplitude change. Now we're going to be multiplying, but that's when we put a number in front. Okay, that's an amplitude change. And the last one we're learning right now is a period change. Okay, that would be like y equals cosine 6 times x, something like that. Okay, anytime you multiply by a number in front of x, that's a period change. Any questions on how you recognize the 4 types?
I think it might have been on homework or something. It was like there was like a parentheses on one of the numbers.
Sure, like this.
Yeah. Would
Yep.
that still be a vertical?
That's still a vertical shift. The only way it wouldn't be is if I grouped the x and the 5 in parentheses.
Okay,
Then it
but
would be a
if
phase
either
shift.
of them is separate, it doesn't matter.
Sure, you could do that. That's not really necessary, but you could write it like that too. Yep. All right.
Wait, can you? Wait, no, I need
The example? All right, so the idea of a period change, you're compressing and stretching on the x-axis. Okay, so next thing we want to figure out is, well, which way does it stretch and which way causes it to compress? Well, that depends on the number in front of x. Let's look at sine 4x. Anybody have a guess how that's going to look compared to sine of x? Is sine 4x going to stretch or compress? What do you think? You thought, Ryan? What do you think?
I think it's going to compress.
You think it's going to compress it?
Yeah.
Anybody think that it's going to stretch it because there's a big number in front of x?
Which one are we talking?
Sine 4x?
Oh.
Think it's going to make it bigger? All right, well, let's take a look. Remember, I said that there's 2 transformations that pretty much what you would think happen is what happens. That's the amplitude. Bigger numbers make it bigger. Numbers smaller than 1, in between -1 and 1, make it smaller. Okay, but let's see what happens when we graph sine x and sine 4x. All right, so let's put that there. That's the original. That's sine x. And the one in red will be sine 4x. Okay, so it did compress it. Okay, that compressed it. So that's important to know, that if we type in a number larger than 1, okay, in front of x, that's when it compresses. If you type in a number between 0 and 1, that's when it will stretch. So like if I did 0.5x, Okay, there's the original. And here's sine 0.5x. It's been stretched out quite a bit. Okay, and how much it stretches or compresses, you can just look at the number in front. Sine 4x is compressed 4 times as much as the original. Cosine 2x would be compressed twice as much as the original. Okay. The 1/2, that's going to cause it to stretch out twice as much. 1/3 would stretch it 3 times as much. 1/5, 5 times as much. All right? Any questions on how you figure out when it stretches or compresses? All right, so since we're stretching and compressing it, we're changing the period. That's why the name of the section is period change. Normally, how many degrees does it take for the function to go from the beginning to the end? What's the normal period of sine or cosine?
90.
Not 90. That means we'd stop about right there. 360. So we said the period of sine and cosine, before you change it, is 0 to 360 or 0 to 2 pi. So what we might have if we compress it, something like this. Now it's doing its entire, all the different values that it's going to do, but it's doing it in half the time. So the period of that one in blue, it goes from 0 to pi. After pi, it repeats.
Does it change in amplitude?
Nope. So I drew that amplitude a little bit off, but yeah, the amplitude would generally stay the same. It would just compress it. So what we want to be able to figure out is what is the new period of the function. Right? So we have a formula that helps us to figure that out. And it's t equals 2 pi divided by omega. So t stands for the period. And to find the new period of a graph, take 2 pi and divide by omega. Omega is the number in front of x. So what I might do on a test is just give you a question like that. You don't have to graph it. I just want to know the period of sine 2x. Okay, so first thing we have to do is identify omega. What is omega in sine 2x? 2. Okay. 2 is not the period. 2 is just what goes in the denominator to find the period. Okay, a lot of people make that mistake. They say the period's 2. That's only part of it. You've got to use that to find the period. So the period here would be 2 pi divided by 2. So what's the period of sine 2x? Pi. So what's happening is sine 2x is going to compress it, and it's going to go through all its values between 0 and pi, instead of 0 to 2 pi. It's been compressed. All right, how about cosine 5x? What would be the period of cosine 5x? 2 pi over what? Yeah. Right? So to get kind of a sense of what that number means, if you change it to degrees, so 2 times 180 divided by 5, that's 72 degrees. So normally the cosine function would have to go all the way to 360 before it's going to repeat. This one only has to go to 72. So from 0 to 72, it'll do its thing, and then it's going to repeat again. Where would the next period end? At 144. And then the next one would end at 216. Every 72 degrees, you're going to get a new period. You don't have to change it to degrees. I just did that so you can kind of visualize it a little bit. Okay, and how about this one? Sine of 1/4 x. Okay, so to find the period, what number goes in the top?
2 pi.
2 pi. This time I'm going to write it as a fraction because omega is a fraction. So 2 pi is in the top. What goes in the bottom? 1/4. How do we do that out?
Why did you?
You only need a common denominator if you're going to add or subtract, but here we're going to divide.
Why did you put on the top?
2 pi always goes in the top.
No, like when you put 2 pi over 1 divided by.
You can put a number over 1, right? That doesn't change it,
Okay.
right? So if I had the number like, say 6 was the answer to a problem, and you wrote it on the test as 6 over 1, that's okay. You're just changing it into a fraction. And you'll see why I'm changing it to a fraction.
Easier to change that way.
Yep, because of how you do this out. How do you divide two fractions?
You
Multiply by the reciprocal. So you've got 2 pi over 1, that's in the top. And the reciprocal of 1 over 4 is 4 over 1. So what would be the period of sine 1/4 x? 8 pi. Okay, so what you've done here compared to the original would have gone from 0 to 2 pi. You've stretched it out 4 times as much. Okay, and that's how you find the period. What if I gave you 3 sine 2x plus pi minus 5? Okay, I'm not going to have you graph one like that, but I might give you one like that and I'll say what's the period.
2x or 2.
No, 2's omega. 2's not the period.
Oh, pi.
The period is 2 pi divided by omega, which in this case is 2. This was more similar to the first problem we did. Okay. What does the negative 5 on the end do?
Shifts the graph vertically.
Which way?
Like
Down 5. Nothing to do with the period. What about the plus pi? What does that do?
Shifts it horizontally.
That's a horizontal shift. Which way? Left or right?
Left.
Yeah, plus is going to move it to the left. That's a phase shift. Okay, the 3 in front, what does that do? That's an amplitude change. And I might also ask you another question here. What's the amplitude of that function? 3. What's the amplitude of that function?
Negative 3.
Still 3. Okay, amplitude is always a positive number. The negative would flip it, but it doesn't change the height. Okay? So any questions on that? Probably have 3 or 4 questions where I don't have you graph it. I just say find the period or find the amplitude. Okay. So now we got to figure out how we graph it. Those 5 key points are going to move, but something's going to stay the same. When you do a period change, what stays the same? Your x's or your y's?
Y's.
The y's. Okay, we're stretching and compressing it left and right. We're changing things horizontally. X goes horizontal, so we're changing the x's. Since the y's stay the same, you can copy them down from the original table. Now we have to find the new x's. Okay, we're going to do this a little differently than we've done the other ones. If you think about the original table for sine or for cosine, what's the first x value in either table? 0. Let's think about what happens if we stretch or compress 0. If you take 0 and you double it, that's like stretching it. Stays 0. What if you take 0 and compress it, take half of it?
0.
Still stays 0. So what happens is your first x coordinate is always 0. The only reason this works is because we're not doing multiple transformations at once. If we were, this wouldn't work. For example, if you phase shifted, okay, the first coordinate would no longer be 0. You'd be shifting it off of 0. So if you do a phase shift at the same time, this idea isn't going to work. Since we're never going to be doing that, this idea simplifies it and it does work, but only for the kinds of problems I'm teaching you. All right, so that's our first x-coordinate. Okay, next thing we want to figure out is the end coordinate. Okay, what is this called when you draw one section of this graph? One section is called the period. Okay? So what we need to do is figure out what is the length of the period from the start to where it ends. Okay? Do we have a formula that calculates the length of the period?
Well, you have the points, so you can figure out on these.
So to figure it out, though, we need a formula to find the length from there to there, the length of that period. And it might not be 2 pi. It could change depending on the problem, but don't we have a way to figure out what the new period is?
Is it 2 pi over omega?
Yeah. To find where the period is going to end, since it starts at 0, the formula t equals 2 pi omega over omega will give you the length of the period, which is the 5th coordinate. Okay, so now we've got the beginning, we've got the end. Okay, what do we know about all the x values in terms of the spacing? They're all equally spaced, they're all the same spacing. So if we've got the beginning and we've got the end, what one would it make, common sense to find next? The middle. Okay, now if we think of these as numbers, okay, if you've got, let's say you had the number 10, and then you had the number 30, how do you find what's in the middle? There's a name for that.
Median.
Not the median, but you're onto the right idea. Yeah. Yep, the midpoint. And what is that called in math? There's a name for doing that. Not the range, the mean. Yeah, the mean, the average. Okay. So if you've got the beginning and you've got the end, and you want to know the point in the middle, just average what's at the beginning and the end, and that gives you right what's in the middle. Okay, so the third x-coordinate is the average of the first and the 5th. Okay, now we have to still find the 2nd and the 4th. Okay, without me giving you any suggestions or hints, anybody think they know how you find the 2nd x-coordinate? Yeah?
You do what you just found for the mean and then the first coordinate.
Yeah, you're going to average what you just found for the 3rd one and the 1st one. So average the 1st and the 3rd to get the 2nd. And we're going to do the same idea to find the 4th. Okay, so let me go back up for a second. To find your 4th x-coordinate, all you're going to have to do is average the 3rd and the 5th. Okay, now this averaging method is one way to do it. It works well with the kind of problems we're going to do, but it's certainly not the only way to do it. There are other ways. But generally, I only show one way because if I show multiple ways, people start getting confused and they mix them up. So we'll stick with the averaging method. Okay, any questions on that before we move on and look at an example? Yep, I can leave. Let me leave that up for a minute.
What's the AG mean? Oh, that's average. So then I was like, what is this?
All right, so those are 5 steps. All right, so first example we're going to do is y equals sine 2x. Okay, before we graph it or make the table, we should find the period of it first, because you're going to need that in a little bit. Okay, this one I think we already did at the very beginning. What was the period of sine 2x? Pi. If you're not sure why that's the period, just go back and look at the example we did. Okay, now let's make our table. Does everybody have the steps on the left? right? So now, what's going to stay the same? Your y's. So we're going to copy all the y's from the original table. What are my original y values for sine? Yep, 0. -1 and 0. Okay, now we need the new x values. Where does the first x coordinate always happen?
0.
It always happens at 0 for the kinds of problems that I'm giving you. Okay, now we need to know what is the length of the period. Where does it end? So we take 0, add the period onto it. So we end up at pi. Right, so now we have the beginning, and we've got the end. Which one do you get next? That's the period. The fifth coordinate is the period.
How'd you know it was?
We did that in an earlier problem, sine 2x.
Oh.
Right, now, what's halfway between 0 and pi? Pi over 2. Yep. And now we need what's halfway between 0 and pi over 2. So remember to average. Okay, if you're not sure and you need to do the average, you add them up, and then you take half of it. That's how you do an average. You add up two things and then take half of it. So what do you get when you do 0 plus pi over 2? You just get pi over 2. What's half of pi over 2? Pi over 4. You just multiply straight across. And now for the fourth coordinate, what are the two values we need to average? Pi over 2 and pi. Okay, the arithmetic here isn't any worse than what you had to do with a phase shift. We do need a common denominator. What's my common denominator? 2. So we're going to double the bottom, double the top. What's pi over 2 plus 2 pi over 2? 3 pi over 2. And remember to do an average, you need to take half of it. What's half of 3 pi over 2? 3 pi over 4. If you write everything with the same denominator, in this case 4, you'll see a pattern.
So you should probably change it.
No, you can leave it like that, but if you want to see the pattern, you'd need a common denominator.
Can you scroll up so I can see the problem again? I'm sorry.
Okay, so y equals sine 2x. And our pattern is 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. We don't see the pattern because we always reduce it as much as we can. And that's our table. Any question on the table? Okay, we'll try one or two more. All right, so next, let's make our graph. Okay, our x values basically are spaced out every 45 degrees. This is 0, 45, 90, 135, 180. Okay, so they're all nicely spaced and nice. Just make sure when you do your graph, you set it up that way. Pi over 4, pi over 2, 3 pi over 4, and pi. It looks a little strange because you don't have the same denominator, but that's fine. For today, your y value is always -1 to 1. And we graph it. So 0, 1, 0, -1, back to 0. Maybe we should have moved some of our labels up above so when we draw the graph, it doesn't go over the label, but it's okay. And that's a compression of sine. Any question on the graph? Question? Okay, what's your question? The x's? So the labeling that I picked, is that how I got them?
I know how you got them, I just don't know how.
So I got them by doing the averaging,
Yeah.
and then I just used them exactly the way they were to label the axis. So that's 0, I didn't label 0. Then I just put pi over 4, pi over 2, 3 pi over 4, and pi.
How do you pile four?
Pi over 4, that's the average of 0 and pi over 2. So we added them up, and then took half. Some people say divide by 2, but taking half of something is the same as dividing it by 2. All right, let's try one. Let's get sine 2x. Yeah, let's do this one. Cosine 1/4 x. First thing I'm going to need is my period, and again, I'm picking one. I think we already did the period when we had a 1/4 in front. What was the period when we had 1/4 in front?
Eight,
8 pi. Yep. So there's our period. Now make your table. Which column is not going to change?
One,
Yep. What are my y values for cosine?
1, 2, -1, 0, 1,
Okay, so we got our y values. My first x value is
0,
0. And the fifth x value is the length of the period, 8 pi.
Oh, so it's given to you on the period?
Yep, that's the period. So for example, if I was going to graph the next period, it would be from 8 pi to 16 pi. There's a new period. Every 8 pi.
Is that given or did you find that out?
That was calculated. We did that earlier on.
Yeah,
How we did it?
I did not do that. That's what we
So if you have a 1/4 in front, you take 2 pi divided by 1/4. When you divide by a fraction, it becomes multiplication
did. Oh,
by the reciprocal. And then 2 pi times 4 becomes 8 pi. Whether it's sine or cosine here, that doesn't change the arithmetic. Still 8 pi. All right, so this is the period we're drawing, from 0 to 8 pi. Next coordinate would be the third. What's halfway between 0 and 8 pi? 4 pi. Okay, you got to keep all these x's evenly spaced. That's why we average. What's the average of 0 and 4 pi? 2 pi. And the average of 4 pi and 8 pi? 6 pi. Yeah, so the numbers worked out pretty nice there. So 2 pi, 4 pi, 6 pi, 8 pi. And again, y-axis for today is always -1 for your lowest value, 1 for your highest. All right, so make your graph. 0, 1, 0, -1, 0, back to 1. Any questions on how I got the graph there? So has this graph compressed or stretched? Stretched. Okay, normally cosine would do its thing between 0 and 2 pi. Now it's going to go all the way out to 8 pi. It's going to go out 4 times as far just to get through one cycle or one period. So it's been stretched by a factor of 4. And let's try this one. Sine of pi over 2x. Okay, this one I don't think we've calculated the period for, so we have to go through and do that. Okay, so to find the period, what goes in the top?
2 pi.
Yep, that's the formula, 2 pi. And anytime omega is a fraction, I always write 2 pi as a fraction, because we're going to end up dividing fractions. Okay, and what goes in the bottom? pi over 2. Okay, we mentioned this earlier. How do you divide two fractions? You multiply by the reciprocal. So it's going to be 2 pi over 1 times what? 2 over pi. So what is the period of sine pi over 2x? No, not 4 pi. Just 4, yeah. Okay, so what happens is you have a pi in the top, pi in the bottom, they cancel, and you're just left with 2 times 2. So we get a very nice number for the period. This is the first time pi has ever canceled out from the x values. So the x values are going to be very nice when we write them. Okay, y values stay the same. Okay, what's my first x value? 0. And my last x value? 4. Okay, halfway between 0 and 4? 2. Halfway between 0 and 2? 1. Halfway between 2 and 4? 3. So we get very, very nice x values here. Since we're going by ones on the x-axis, you don't need to label it if you don't want to. Anytime you're going by ones, you don't have to label. Most of the other times you do, though. I'll label it just so there's no confusion. So we got 0, 0, 1, 1, 2, 0, 3, negative 1, and 4, 0. And there's our graph. Hey, is that a stretch or a compression?
Stretch.
Well, what would it normally go to from 0 to 2 pi? What's 2 times pi? 2 times 3.14? 6.28. So normally it would go all the way to 6.28. So this has been compressed a little bit. Not a lot, but a little. Right, just barely. Okay, any questions on that one? Okay, so that's how you do a period change. Okay, that's how you get the table, and that's how you do the graph. Okay, so the last couple things I want to look at are just some applications of frequencies, and we'll see what we have time for. Okay, the first one is called, it's a device called an LRAD. Anybody ever heard of an LRAD before? LRAD? Okay. Yeah, what do you know about it?
I just think I've heard it.
You've just maybe heard the term before? So an LRAD stands for, it's a long-range acoustic device. And what this device basically is it's like a spotlight or like a laser beam for sound. So if you think of a laser and you shine it, it's not like a flashlight which lights up a big area. Okay? It's kind of like a laser that focuses in one spot. So an LRAD, it's kind of like a specialized speaker where if you aim it at somebody, that person hears it very well. Okay, but the person behind the speaker, they can't really hear it. The person's off to the side of the speaker can't really hear it either. It's a very focused sound. Okay? So what you can use it for is finding, basically you can look, if you had to talk to a crowd of people and it was like a big crowd, you can direct your voice right to that crowd and they'll hear you very clearly. They can also play certain frequencies over this device. Frequencies that aren't very pleasant to be around. And that would cause usually a crowd to disperse and want to get away from that sound. All right? And that's another use for it. So I'm going to show you a little clip that demonstrates some of the uses for it.
In response to the terrorist attack on the USS Cole in October of 2000, American Technology Corporation created a device like no other. LRAD, the long-range acoustic device.
A wave of the future.
A high-tech tool developed by the military.
A high-tech sonic weapon.
Long-range acoustic device, or an LRAD.
The long-range acoustic device, or LRAD, is like an audio spotlight. When you're standing alongside of it or behind it, you can carry on a normal conversation, but get directly in its beam, and the sound becomes almost painful.
Because of its weight and size, the LRAD is easy to transport, easy to set up, and mounts almost anywhere.
Cruise passengers now barely escaping that pirate attack.
We're learning more about that stunning pirate attack.
This magnificent cruise ship attacked off the coast of Africa by 21st century pirates.
The LRAD's usefulness was most recently demonstrated in November 2005 when pirates attempted to attack a cruise ship off the coast of Somalia.
It has 26 languages and about 100 different remarks like put your hands on your head or lie flat on the ground or turn around and do such and such.
The system clearly enables us to enforce the Naval Vessel Protection Zone at all times.
The fact that an individual was informed of the reasonable consequences of his actions and continued to defy legitimate authority, they are personally responsible for whatever happens next.
Whether initiating communication or warding off unknown adversaries, the LRAD has proven effective more than 80% of the time and has saved countless lives in the process. From American Technology Corporation, LRAD, the long-range acoustic.
All right, so they showed a few uses there. I think the New York City Police Department, they had it, and trying to disperse a crowd with it. It's not a totally, I want to say, a weapon that won't harm you. There's another clip I have, which I'm not going to show today, but it explains how it can cause permanent deafness because it is a very, very loud sound. If I play the frequency for it, you can actually see it on the computer. I'm going to turn it way down so it won't be too loud. But you can see if you look at the screen, you're getting a nice kind of, almost like a sine or a cosine wave. I think actually though there's two frequencies being played there because it kind of sounds like you're hearing a couple different noises there. Okay, but that's the frequency, or that's the sound of an LRAD. Right, so the other thing I want to take a look at, okay, besides using it for kind of like a military use, is more of a use that we use it for every day. And that's called dual tone multi-frequency signaling, Dtmf. Anybody ever heard of that before? Probably haven't heard of it as called that, but you do use that. And it's basically the idea of how your telephone works. All right? If you go to this page and you scroll down a little bit, okay, there's a chart, and it shows you basically every button on the phone is a combination of frequencies that it's generated. It's not one, it's two. That's why it's called dual tone. So for example, when you press a 1 on the phone, there's two frequencies being played, 1209 and 697. Okay, and earlier my computer wasn't working, but let me see if I can get it to work now. Okay, so this is a 1209 and only a 1209. Okay, I'm not playing the other one. Okay, that doesn't really sound like a button press on a phone. All right, let me play 697. Okay, I'll let you hear what this one sounds like. Okay, again, that doesn't really sound like a button as well either. But then when you play the two together, you get this kind of effect that will sound like what you're used to hearing when you press a button. Okay, that's when you press a 1. Okay, every sound that you hear over the phone, whether it's a dial tone, the ringing sound, the busy signal, they're all frequencies. So the busy signal happens to be the 480 hertz combined with a 620. Yeah?
Is it true that like every number has like a different tone?
Yeah, every single number on the phone is a different tone, as described by that grid. So here's 480 and 620. What did I say that was?
Busy.
That's the busy signal. And this is one that pulses. So it doesn't just stay, it kind of pulses on and off. Okay, so there's your busy signal. What else we got? Let's say your dial tone. Okay, the dial tone is basically like a background sound. It's there all the time, for like a corded wall phone, not a cell phone. But the dial tone is basically there, and it's waiting. It's waiting for you to start pressing buttons. Okay, so here's your dial tone, 350 and 440. And if you change it just a little bit, okay, throw that frequency off, say from 440 to 420, it doesn't sound quite right. So you hear it and it's like, wait a minute, something sounds a little off. Okay, so what I can do with that is if I call my voicemail, it'll say press 1 to enter your personal options. Okay? Now, whether I press a 1 or the phone hears a 1, it doesn't know the difference. So what I'm going to do is I'm going to call it, I'm going to generate the frequency for a 1, and then it's going to go into my personal options. And then I think it'll say press star to exit, and then I got to press star one more time. Okay, something like that. So whatever frequencies it tells me to generate, I'll try to generate. But it's got to be pretty quiet to make it work. If there's a lot of other sound, it can't hear the frequency since I'm pretty far away. All right, so first let me turn it up so you can hear it. Okay, and actually I think it asked me to press a 4 to enter personal, so it's 1209 and 770. Okay, let's see how that sounds. Okay, so there's a 4. All right, let's call it and see if we can make it work.
You have no messages. Main menu. To send a message, press 2. To check receipt of a message, press 3. To change your personal options, press 4. To disconnect, press star. Personal options. Turn notifications on or off. Press 1 to change administrative options. Press 2 for green or recorded name. Press 3 to change notification options. Press 4 to exit. Press star. You have no messages. Main menu. To send a message, press 2. To check receipt of a message, press 3. To change your personal options, press 4. To disconnect, press star. Goodbye.
All right, so just by generating the right frequencies, you can control, a voicemail, or with this kind of phone, like a wall phone. If I could generate the buttons fast enough, then I could make a phone call without pressing the buttons.
Oh my gosh, yeah, that's great technology. So it's more complicated.
Question, yeah.
It was more by the noise than by the actual pressing of the button.
Yeah, so with a cell phone, sometimes you don't hear it when you press it. Okay, you see the number on the screen. So what's happening there is the signal of the frequency is still being generated internally, but it's not being played over the speaker. Okay, so the phone doesn't actually have to hear it if you're pressing the buttons. So that's a little bit different the way it generates the sound. Okay, so that's that. All right, and the last thing I'm going to show you has to do with music. All right, so the idea of music is all notes in music have a certain frequency to them. Okay, and overall, our hearing can't really distinguish between sounds that are very close. For example, if I play 900 hertz, okay, let me turn it down a little bit. Okay, whoops, I didn't hit enter. Okay, there's 900. And then if I play 901, to me it sounds pretty much the same. Maybe if I played like 900 and 905, you might start to hear it. Okay, but the idea is that our ear can only hear so many different notes that actually sound different. Those are technically different, but they don't sound different to our ear because we don't have a sensitive enough ear. So there's a question that since we can only hear so many notes, and there's only so many different ways you can arrange the notes, okay, let me kind of simplify it. Let's say the only notes that existed were A, B, C. Well, there's only so many ways to arrange note A, note B, and note C. You have ADC, ACB, BCA, BAC, all the different orders. Okay? Eventually, would there ever become a point where we've taken all the notes we have, which is a lot more than 3, we've arranged them in all the different ways you can, and there's no more new music? Will we ever reach a point where we've generated all the kinds of melodies that we can have? Right? And we'll take a quick look at what this video says about that. And 2 concepts are mentioned in this video, the idea of infinite and finite. Infinite means that there's no end. Okay? You can't count how many there are. Finite means it might be a big number, but it's countable. So for example, if I said how many grains of sand are on all the beaches in the world, it's a lot, but it's not infinite. It is finite. There's a certain number of grains of sand. Okay? It's huge, but it's not infinite. Okay? So let's take a look at this video. We're going to watch about maybe 4 minutes of it, and then I'm going to switch to one other video that he talks about, and that'll be the end.
And the iTunes store contains 28 million different songs. Last.fm carries 45 million songs, and the Grace Note database of artists, titles, and labels contains 130 million different songs. That's a lot. If you were to listen to all of the songs in the Grace Note database one after the other in a giant playlist, it would take you more than 1,200 years to complete. But since there are a finite number of tones our ears can distinguish, and because it only takes a few notes in common for 2 musical ideas to sound similar, will we ever run out of new music? Will there ever be a day where every possible brief little melody has been written and recorded, and we are left with nothing new to make? A good rule of thumb might be to say that if modern recording technology can't distinguish the difference between 2 songs, well, neither could we. So let's begin there, with digital downloads, MP3s, CDs, and a calculation made by Covered in Bees.
Is that part of the test on you?
Digital music is made out of bits. Lots and lots of bits. But each individual bit exists in one of 2 states, a 0 or a 1. Now what this means is that for any given, say, 5-minute long audio file, the number of possibilities, mathematically speaking, is enormous, but mind-blowingly finite. A compact disc, which samples music at 44.1 kilohertz, is going to need about 211 million bits to store one 5-minute song. And because a bit can exist in 2 states, either a 0 or a 1, the number of possible different ways to arrange those 211 million bits is 2 to the 211 millionth power. That value represents every single possible different 5-minute long audio file. But how big is that number? Well, let's put this in perspective. A single drop of water contains 6 sextillion atoms. 6 sextillion is 22 digits long. It's a long number, but the total number of atoms that make up the entire Earth is a number that is about 50 digits long. And estimations of the total number of hydrogen atoms in our universe is a number that is 80 digits long. But 2 to the 211 millionth power, the number of possible different 5-minute audio files, is a number that is 63 million digits long. It is a number larger than we can even pretend to understand. It contains every possible CD-quality 5-minute audio file. Inside that amount is everything from Beethoven's Fifth to Beck's Loser. It even contains a 5-minute conversation you had with your parents when you were 3 years old. In fact, every one of them. It even contains every possible conversation you didn't have with your parents when you were 3 years old. But it is finite, not infinite. It's cool to think about, but it doesn't come very close to answering the question of this video, which is how many possible different songs can we create and hear the difference between. So for that, we're going to need to narrow down our hunt.
So he goes through some calculations and narrows it down. And he concludes that we'll never run out of new music. But then he gets to another point, which I want
Everything,
you
too,
to hear.
Ferris lepidoptical measure is how many of 8 note whole half notes. The melodies, under this definition, huge number, way bigger than the total number of songs, though we will never run out of new music. But here's the rub. If that's the case, why are there so many commonalities between songs, even across hundreds of years? How come so many songs kind of sound the same?
So he's saying if there's so many melodies to pick from and so many different notes, why do a lot of songs sound similar?
If we have more possibilities than we could ever exhaust, why is Twinkle Twinkle Little Star, the alphabet song, and Baa Baa Black Sheep all the same melody? My Country 'Tis of Thee and God Save the Queen, interestingly enough, are the same song. Love Me Tender is exactly the same as the old American Civil War song, Aura Lee.
Sunshine came along with you, and I always will.
And a seemingly uncountable number of songs merely sound like other songs. The SpongeBob SquarePants theme has a very similar cadence to Blow the Man Down. SoundsJustLike.com is a great resource for exploring this further. It'll show you 2 songs and how they sort of sound alike. And when it comes to musical chords, it's almost as if there's no variety at all, as was famously shown by the Axis of Awesome's 4 chords.
Oh, I love this.
So,
Four chords the best.
That's where we'll end with that, and
Do those.
you can hear that video.
Yeah, if it starts to believing, watch it, and the costume play. Yeah, it's a female song with the same chords. Check it out.
Okay, so the point of that is all those different songs you just heard using the same chords, same notes, in other words, very similar frequencies. Okay? All right, so you guys have your worksheet. You got your 2 take-home problems for the test, and you'll finish the test tomorrow in class.